Hello. This video we're going to focus on building a facade, a diagrid facade, figuring out how to quantify it, figuring out how to rationalize it. This is meant to be in addition to the stuff we've talked about regarding construction pricing and also ways of building out systems that are logical and rational so we can easily translate them into other platforms. So I'll just jump right into it. We're going to do this all in Grasshopper. And in a later class, we'll work on connecting this into some of the other stuff we've done and optimizing it and rationalizing it. But for now, what we'll do is we'll extract quantities and build a rational facade. So I'm just going to start by bringing these curves in. I'm going to just make a curved facade to show the flexibility of this. Let me make this window a little smaller. So I'm going to just copy this, Control-C, Control-V. Set one curve here, set one curve here, loft this across, just take these two curves, loft it, make a surface, nice and easy. For now we'll try to actually keep it a little bit more, let's make it more sort of flat and then we'll edit it later. Have somewhat flat surface. Actually, pull this point down so it's flush there, pull this point there. Now we've got basically a flat surface. Okay, so let me just get this focused. Okay, so then I'm going to use a shortcut to make this into a diagrid. I'm going to use the lunchbox tool and the panelize function so I can load in my surface. And it's going to create some panels. I'll hide this. So now I've got my diagrid panels. I'm going to set up a slider and make it go from 0 to 30. So we'll just do 30 divisions from now. And I'm just going to copy this because I'm going to feed it into the U and to the V. So here I can make some more divisions. We'll make it a little bit taller than it is wide, so we get something like this. We might even want to just move this in a little bit to make it a little bit more diamond in the vertical direction. Now what I can do is I can grab out the different surfaces that are associated with this. So this breaks it down into my diamonds and my triangles, which are at the edges. I'm going to operate on my diamonds for today, so I'm going to just hide these for now, and I'm actually just going to hide the triangles. So now I have my diamonds. And as I mentioned in class, we want to be logical about how we construct our systems so then we can translate them and evaluate them. So rather than trying to just do some operations on these surfaces, I'm going to break it down into construction geometry that it's easy to identify and then work with that. So I'm going to use what's called a BREP. It used to be called BREP components. It's now called Deconstruct BREP, which is here. Grab this surface. I've got vertices here now. So I want all the vertices for each one of these panels. And I'm going to use those to construct my geometry. So I'm going to actually use a list item component. And I'm going to plug the vertices into there. And I've got a bunch of lists now, 275 panels. Each one has 4 vertices associated with it, which is each one of the 4 points of the corners. And then I could just come down and add this. So this is going to give me list item 0, list item 1, list item 2, list item 3, because 0 is what's coming into here. If I was to plug a different value into here, this would be I, this would be I plus 1, and so on. We can actually go the other way and go in negative, but this is a good way to break out a bunch of different components from one list item starting with a certain member. And then what I like to do is identify these points individually so that again we can use them later and easily identify what they are. It can get a little bit lost in the definition if you don't identify things. I find you kind of then start to click on things and try to see what they are, and especially in a situation like this where there's actually, the left panel of this side is the right of this one, or I'm sorry, the left the left of this one would be the right of this one. So we would start to get overlapping information, and you know, we can't just visually identify them as we go. So by labeling them is very helpful. So I can see here that these are all the left, right? It's not the top, because then those would be highlighted. It's not the bottom, because those would be. It's not the right, because then the right side here would be highlighted. So this is the left side of all the diamonds. So I'm actually going to just call this point left. This is all of the bottom. So you see it's not the top, it's the bottom. So I'm going to just call this point bottom. Okay, this is all of the right. And this is all of the left. All right, now that I have these, I can operate on these. So I can almost just sort of like hide everything from here back, because now I only care about these points. This is what I'm going to be using to operate on going forward. So this stuff can be hidden. And I'm actually going to reconstruct some edges here. I could pull these edges off of here and use these, but I like to reconstruct them so I know exactly which is which. So like going from the left to the bottom, I'm going to do a line component, and it's this one with the 2 points on either end. This is a line AB component. So this will connect point A and point B. So I need a left curve. I need a bottom to right. I need a right to left. And then I need a left to left. I'm sorry, this should not be left. This should be top. There we go. So now this goes top to left. So if I highlight all these, it closes up a full grid. So if we look here, I've got my bottom to left point, my bottom to right, my right to top, and then my top to left. So that's good. I've got all the edges of those curves. And I actually, because for the sake of this exercise and how I want this facade to be designed, I actually want this to be consisted of a series of triangles. I don't want any curvature in it. So if I rotate this, you'll notice we'll start to get diamonds, but these diamonds, if I was to create surfaces from them, would actually have curvature on them. And I can illustrate that by doing a 4-point surface, which we're going to use this component later. 4-point surface. And if I was to take all these and plug them all in, I have these surfaces. And if I was to take and do a flatness check, which is another great component from Lunchbox, my deviation from flatness here should be a value let me see if I actually pull this a little bit. So you know what, it's actually, am I wrong about this? I don't think so. These should have curvature associated with them. Maybe my flatness check is not working. We're going to use this elsewhere, but let me just amount of flatness deviation. Projection planes are here. So maybe if we look at these projection planes, these are what those planes would look like when they were projected. So if I want to see these, I can actually just hide all this for now. Sorry, it's not that, it's this. It's the flat panel projections. So maybe I am wrong that these are all non-curved. Anyway, I'm digressing. For the purposes of this exercise, let's just assume that they are all, you know what, I'm sorry, I'm going to do one more thing. Maybe because it's a ruled surface, they're not. So let me copy this back. And let me do, loft will actually be I'll include this in the loft. Oops. Now we have a rounded surface like that. Let me see if this, yeah, so these, okay, it might have been because it was a ruled surface. So these will deviate now from flat. Yeah, see, so now we have a deviation between flatness. So we're going to use this really funky looking surface for this. Let me just flatten it out a little bit so it's not too intense. And if I preview this, you'll see we have our 4-point surfaces, but these are actually curved, as we just illustrated with the flatness check. So I don't want there to be any curvature in my panels because I want to make this up out of flat panels. So what I'm going to do is turn these back on. I'm going to, and let me turn this off back here, I'm going to triangulate these panels. And the way that I can do that is I can, to illustrate that, I can do a line in between the right and the left. So that's what that looks like. I'm actually not going to use this line, so I'm going to just turn the preview off, but I just wanted to kind of illustrate where we're going to cut the panel. And I'm going to use that same 4-point surface component. And I'm going to do left, bottom, right. And I'm going to make a triangle out of that. So I'm going to do left, bottom, right. And the 4-point surface component actually can function with only 3 surfaces, 3 points. So we'll just leave it at that. And then I will cut and paste this, and I'm going to do another one, which is left, right, top. So let's go left, top, right. So now we've got those. And you see, when I hide the preview a little bit, you can start to see, you can see how you get the little facets in there. But essentially it's made up of flat surfaces now. It's no longer made up of curved diagrids. But architecturally, if we wanted to express these lines, we could do that. So maybe what I'll do is I'm actually going to change the preview of this so we can see this a little better. And I'm going to start doing some custom previewing. So this is my glass panels. So all my glass goes into here. So I'm going to call geometry glass panels. And then I'm going to go to geometry here. I'm going to pull 1, 2, 3, 4 into there. And this is my geometry mullions. And we could do something like pipe this or sweep a rectangle on that to give it some thickness. But when we're analyzing it, I don't want to do that because it's just going to add unnecessary complexity. That's something that we could do later, preview, and if we want to do a more in-depth analysis, we could do it with that, but for now, we don't want to do that. And I'm going to do a custom preview, and I'm going to put this as with a swatch. We'll make the glass, you know, a blue color. Maybe give it a little bit of transparency. Do that, hide that. So now we've got our glass. All right, cool. And then our mullions, I'm just going to cut and paste this whole thing, plug that in, make this black and fully opaque. And if we move these around, the facade will update and so on, and we can come back and adjust the slider and have it update, right? Cool. So the next thing I'm going to do is I'm going to add a detail to this that's kind of like a sunscreen that we can then play around with later and adjust based on different parameters. But the way I want to do that is I want to do that popping out from the surface in 3D. And I'm going to do it so that it essentially will move along an arc to get us different looks. So to do that, I actually want the center point of this line because I'm going to build my arc based off of that, based off of the center of the panel. So I'm going to use what's called a point on curve component. And I can plug this in, and this will just essentially give me, this is hidden, but this is basically just giving me a point along that curve. I'm going to make it the midpoint, and so then I have that. And now I need to be able to figure out the normal to this. Because it's made up of two panels, I'm actually going to do a little trick where I'm just going to do a plane of this, and if you just plug a surface into a plane component, it'll give you the planar surface. I'm sorry, the plane that's the average of the points of that surface. So now I have my two planes, and just to keep this apart from the glass construction, I'm going to move all these operations up here. And I'm going to deconstruct these planes, which will give me the origin and the vectors associated with it. And I have two z vectors, and if I want to get the average of those, I can just add those up, and it'll give me the vector, the z vector off the surface that's in between them. So now, if I do a line that originates from that center point, I can then start to control the distance of the arc from the surface of the panel. So I'm going to use the line SDL. So the line start is here. The distance I'm going to put on a slider between 1 and 100. So I'm just going to hit slider equals 100. I'm sorry, that goes into the length. And the distance, this, if you look, this is actually providing a vector to us. It's not providing just a single number. So I can pull this into direction, and it gives me not what I was hoping for. Is this giving me... Why is this wrong? Let me just open up my little reference document here to see what I did differently in here. I had oh, I'm sorry, it's not deconstruct, it's deconstruct plane. Did I use deconstruct plane? Yes, I did. Deconstruct plane, Z, I add those up. Start, direction is the addition of those two. That's weird. It worked when I did it here. I'm going to try to just use the Y's, see if that works. Yeah, that's working. It might just be something with how the plane is twisted, that the vectors that it's using are not oriented normally, but it seems like if I use the Y's it works. Sometimes the planes, depending on how the surfaces are being built, get a little bit twisted, and if you use a different vector it'll help. So now I have these, and I want my arcs to always be a consistent distance from the surface. So I'll set this for 50 for now. We can change that. And then what I'm going to do is take the end point of this line, and I'm going to label that. And I'm going to call this arc center. So again, we want to know what these all are. We want to give them names. And like when I've done that here, I can essentially create a line between the end of this operation and the beginning of this one. It's because like I'm just working with these points now. So I can define what that is, and then I'm going to do an arc 3 points. And my start, I want that arc to go from the top to the bottom of the panel and go through there. So my arc start point is going to be the bottom. The middle point is going to be the arc center, and then the end point is going to be the top. So now I've got that arc, and if I adjust the depth, which that might be too far out, I can bring it in, and now I've got that arc that'll help me control the panels that are going to be the sunscreen that go in or out of the surface. Alright, so the next thing I'll do here is I'm going to start to construct the metal panel sunscreen that goes on top of this. And this is going to be easy. I want it to go from top to left to the arc, and then top to right to the arc. Again, it's just going to be constructed of triangles. So, oh, you know what? I'm sorry, I forgot one step. I'm going to do, I want the point on this arc, which dictates where that sunscreen is, to change and be variable. So what I need to do is start to set up that logic, and then later we're going to plug in some values to make that work. But I'm going to do what's called an evaluate curve and plug in these arcs, and then I'm going to put this on a slider so you can see what it looks like. But if I just plug it in like this, it's going to be 0.25 inches off the end, so that's 0 up to 1. That's not enough, right? It's too small. What I can do is I can reparameterize this curve if I right click and reparameterize. And what that means is that it'll actually evaluate this on a scale from 0 to 1 rather than a scale from whatever the length of it is. There are many ways I could do this. I could evaluate the length of that curve or you know, pull the length and then do some division. But this will just allow me to understand that I'm working within a scale of 0 to 1. And when I start to create logic to build out the facade, I can do it within the context of that. So let's just put this at like somewhere here for now, it doesn't matter. And then I will start to build these out. And I'm going to call this metal panel top. Okay. So now, like I said, we can start to do that that sunscreen that's coming down from the top. And so I'm going to connect top, left, metal panel top, which is here, then top, left, top, right, metal panel top. And we're going to use the same 4-point surface component. And we're going to go from top to right, from top to left to metal panel top. Control C, Control V, we're going to go top to right, so I'm just going to swap the right out for the left, metal panel top. So now, if I zoom out, I have these little sunscreens that are hanging down at the top. And similarly, I'm going to plug these in. I'm going to call this geometry metal panel. And then I'm going to hide all this. And custom preview this as a sort of like a gray. There we go. So this is cool, but you know, it's all fixed. We want this to be variable. So there's one last step, which what I'm going to do is I'm just going to create a point. And there's lots of ways to make this variable, but we'll just do this with an attractor point for today. But if I grab this point I've got that point now, and I'm going to come back and I'm going to use this center point of the panel, which is coming from this here. And you know, again, to make this all clearer, I might do this. I might plug this into there. If I hold down Control and Shift, I can grab something and plug it in somewhere else. And I might call this panel center point. So now what I want to do is get the distance from this point to the panel center point, so I can use this as an attractor to determine the openness. So I'm just going to do what's called a pull point component. This is good for measuring the distance to a point from a bunch of different pieces of geometry, but it's good for like lots of different things. You can use curves, you can use surfaces. It's very generic. You can do point CP, which is like point closest point, or yeah, closest point. This is very generic, number one, so it works with everything. And then number two, so if you want to switch later and go from a point to a curve, you can do it. Number two, it also allows you to plug multiple things in, and it'll find the closest element and measure to that. Whereas point CP will not, by default, measure to multiple different things. You can do it with some tricks, but this one, it just sort of out of the box works that way. So I like to use this for everything. The point to search from is here. The geometry that pulls is going to be all of these center points. And so if you wanted to visualize that, it would look like this. It would look like this. It's going to all of these. Now that's basically that, just giving me all of those rays. This distance is basically the lengths of all of those. So if I was to do a length component on here and do a panel, I should get the same values. Yep. So it's essentially just giving me, it's essentially drawing a curve between those two, a straight line, and giving me the distance. So you could also do it using this technique that I just did, but the pull point kind of gets us to exactly where we want to be right away. And as I mentioned before, I want all of these values to be relative between 0 and 1. So what I'm going to do is I'm going to remap these numbers. But before I do that, I actually need these all to be in one list. But I have all of this stuff. I haven't really gotten too much into the data trees here, but it's working very nicely. And all of the values are associating with each other nicely. So I'm going to show you how to do this. I'm going to use a flatten tree component here. And I'm going to take these distances, I'm going to flatten them. I'm going to remap them so they're between 0 and 1. So if I look at all these values flattened, it's just a bunch of distances. The value to remap is this. The source domain is 0 to 1, and the target domain is 0 to 1. I actually want the target to be, we'll probably do 0 to something different. But the source is not 0 to 1. The source is actually what all these numbers are, the highest and the lowest. So you can use a bounds component, which will give you the highest and lowest number in a list. That's my source domain. And my target domain is, I'm going to construct a domain. Not squared. It's this one. Plug this into my target. Make this on 2 sliders, and I can just use the default 0 to 1 with 3 decimal points. And what you'll see is this will be percentage of openness. So at my lowest, let's say I want it to be 10% open. Oops, let's do 0.10. And at my highest, let's say I want it to be 0.9% open. So I can see now it's taken these numbers and it's remapped them so that they are relatively the same dimension or distance from each other, but now they are going between 0.1 and 9. And if I change the scaling here, you'll see it'll change this. But this is a good way to be able to control everything as a percentage rather than a full value. And so the last thing I need to do in order to make this work is I'm going to unflatten this. So what unflatten tree does is exactly what you would expect. It takes it and it unflattens it and brings it back to the original organizational structure that it had before you flattened it. So the tree to unflatten is actually all of these. And the guide tree, we're going to come back to before we flattened it, and we're just going to grab this, and this is the tree we want to go back to. So now it's basically taken that and put it back to the logic that we had the first time. So the last step to all of this is I'm going to take this, and rather than using this slider to control those openings, as you see there, I'm going to take this, and I'm going to plug this into there, and now I've got variable. And so the closer it is to the point, the more closed it is. And so you could actually use a vector or something here, and you could use it as the sun's rays. But as I move this, you'll see the openness will change. So it changes depending on that. And if I change this, it'll change. And I can actually adjust. You know, let's say at the most I want it to be 80% open. I can change this to 0.8, and you see that these will actually get a little bit smaller. So if you see as I slide them, they'll open more or less depending on that. And I can set the, you know, maybe I want them to be more open than 90% or than 10%, or maybe I want to go less. If I go down to 0, it seems to actually not break. I was thinking that it might, but I could actually do it 0 to 100% as well. And so the most closed panel is going to be 100%, and the most open panel is going to be 0%. And essentially it's always sliding along that arc. So it's going to move in and out of the facade, but it's always based on the location of that arc, which is consistent. All right, cool. So now that we've gotten this fun part done, we can do the geometry analysis on it. And this is super straightforward, but all I'm going to do is do an area component. So I'm sorry, I'm going to do an area component, right? And then I'm going to flatten this, because right now it's actually just giving me them all in individual tree branches. I want to flatten this, and I'm going to do a mass addition. Not all inputs. What's happening? This should be not all inputs. It might be it's weird. I don't know if there's some value that's coming out of here that's very strange. I don't know what that error is, but I'm not going to worry about it right now. This is in scientific notation because it's a very large number, because we're using inches. I can do a division component, divide this by 144, and then plug that in. So now I know I have 17,062 square feet of metal panel. Now if you offset these and give them thickness, it's going to be different. This is again for analysis purposes, but if you do offset this and give it thickness, this area is going to be probably double or even higher depending on how much you offset it, because it's going to count all the surfaces of that offset or that extruded surface. So when I'm doing analysis like this, I like to keep it flat and keep it keep it just planar. So what I can do is I can actually copy this whole thing and paste it, and I'm going to plug my my glass into here, which is here. my glass panels into there. So that's my total glass square footage, and it makes sense that that would be higher than that because the glass is covering 100% of the facade and this is covering a smaller percentage. And the last thing I'll do is for my mullions, which are back here, I'm going to actually do a length component, and I'm going to do the same operation, but I'm going to divide it by 12. So let me just grab all of this, divide it by 12 here, and now I've gotten my linear feet of mullion. So we want to make sure whatever unit we're using is consistent with that type of geometry. And if I pull all these together, and as I flex my surface, if I pull this, you'll see all those values will update automatically. And if I come and I maybe move some of the, I'll just pull these up for now. It's not very good Grasshopper organization, but if I start to pull these, you'll see that those numbers change as well. Right now the metal panel is the only one that's changing because it's the only one that's related to that. And again, I'll grab these, it's going to be messy, but I'll grab these, which is my divisions, and the areas are probably not going to change that much. Actually the metal panel will, the glass probably won't, but the mullion dimensions might change significantly. Yeah, so you see the mullion dimensions are changing significantly. I guess the glass is too. It's getting a lot less curved, and it's going to lose some of its thing, and I guess because a lot of them are becoming, the triangle square footage is getting bigger, so we're not counting that right now, but that's will also update all of this. Alright, so that's it for this. This will tie into some other stuff as we get further into the semester regarding optimization and things like that. Thank you.